Welcome to this video on full-chain CCUS project execution, lifecycle assessment, and ESG accounting. We will cover front-end engineering design stage gates, ISO 14040-44 frameworks, process safety, and corporate ESG disclosure mandates. It's prepared by Dr. M. Fahed Qureshi from National University of Singapore. In this video, we will explore three core learning objectives: mastering project execution stage gates, quantifying lifecycle assessments for greenhouse gases, and evaluating ESG and process safety protocols for carbon capture projects. Next, we will focus on project execution and front-end engineering design, or FEED, stage gates. Front-end loading, or FEL, occurs in three stages: conceptual feasibility screening, pre-FEED for technology selection, and detailed FEED for final procurement, contracting, and investment decisions. Plant engineering integration is critical. This involves complex tasks like steam integration, managing space constraints in brownfield sites, and planning electrical tie-ins for high-power equipment like CO2 compressors. Different EPC contracting models carry varying levels of risk. Options range from single turnkey contracts to split package approaches and utility models, each with distinct implications for owner risk and cost premiums. Interface risk buffers are often necessary, sometimes reaching a 15% premium. Managing these risks, such as preventing off-spec gas from entering pipelines, requires automated monitoring and robust safety systems. Commissioning involves two main stages: cold commissioning, which includes pressure testing and signal validation, and hot performance testing, where real flue gas is used to verify operational efficiency and emission limits. Now, let's transition to lifecycle assessment standards as defined by ISO 14040 and 14044. The ISO 14040 LCA framework consists of three steps: defining the goal and scope, establishing the inventory of material and energy inputs, and calculating the overall environmental impact using global warming potential metrics. LCA system boundaries can be defined as cradle to grave, covering the entire chain from extraction to long-term storage, or gate to grave, which focuses specifically on the emissions within the facility infrastructure. The net carbon avoided calculation must account for parasitic energy consumption, transport emissions, embodied energy in materials, and potential fugitive emissions. This footprint breakdown shows how penalties for reboiler steam and compression electricity reduce the gross capture volume to a final net climate benefit. Embodied supply chain carbon includes emissions from the manufacturing of structural materials like steel and concrete, as well as the production and degradation of chemical solvents. Finally, we must consider environmental impact assessments, or EIA, which address broader ecological concerns beyond carbon, such as ecotoxicity. Moving on to atmospheric amine emissions, volatile amine solvents can degrade into toxic compounds like nitrosamines and nitramines when exposed to flue gas impurities and oxygen. Acid wash scrubbing is utilized to neutralize these vapors, keeping emissions below 0.5 parts per million. Our emissions mitigation target aims for a strict SUB 0.5 ppm volatile amine limit. Modern permits enforce these standards, supported by advanced dry bed Brownian diffusion filters to prevent aerosol drift. Water footprint management is essential for sustainable operations. We must account for cooling water duty, maintain strict thermal discharge limits, and integrate zero liquid discharge systems to recover water and eliminate toxic effluent. Managing hazardous waste involves strict logistics. Waste streams like reclaimer sludge, spent solid sorbents, and activated carbon filters are classified and processed through high-temperature incineration, hazardous landfilling, or off-site thermal reactivation. We now address quantitative risk assessments, or QRA, and process safety, which are foundational to secure project operations. Computational fluid dynamics, or CFD modeling, is used to understand heavy gas physics. Since CO2 is denser than air, it requires precise modeling for buffer sizing to maintain safe distances around high-pressure pipelines. Understanding dense CO2 hazard physics is crucial. A pipeline breach causes cryogenic flashing, creating freezing dry ice snow. We also track asphyxiation thresholds to ensure worker safety against CO2 exposure. Process safety utilizes HAZOP and LOPA methodologies to evaluate risks and establish necessary safety integrity levels for our facility components. Emergency isolation systems are critical. These include automated shutdown valves for rapid pipeline isolation, acoustic alarm grids for leak detection, and strictly enforced zoning setbacks for residential areas. Next, we will cover ESG accounting and sustainability mandates, which are increasingly vital for corporate transparency and compliance. Under the GHG protocol, we categorize emissions into scopes: Industrial emitters manage Scope 1 and 2, while transport and storage operators have distinct responsibilities, including Scope 3 service reporting. By 2026, IFRS 2 and CSRD directives will set a global baseline. These mandates require companies to disclose climate transition risks and prove their CCUS projects meet Do No Significant Harm criteria. Article 6 carbon offsets are governed by UN registries. This includes corresponding adjustments to prevent double counting and ensuring that internationally transferred mitigation outcomes meet strict durability standards. Digital twin technology enables real-time life cycle assessment. By integrating live sensors and simulators, we can automate carbon credit issuance and optimize facility performance against energy prices. Finally, the construction stage involves complex logistics for modular delivery and brownfield integration. We conduct stage gate audits to ensure structural integrity and safety before final commissioning. Artificial intelligence is revolutionizing predictive maintenance in CCUS. Neural networks analyzing continuous fiber optic acoustic data detect micro-leaks and structural strain early. Meanwhile, vibration analytics on supercritical pumps help prevent unplanned plant trips and venting events. The decommissioning timeline encompasses well plugging and abandonment using acid-resistant cement, 50 years of post-injection site care, verifying geomechanical stabilization with 4D seismic monitoring, and the final formal transfer of long-term storage liability to the state. This integrated execution matrix provides a structured framework for managing the various components and phases involved in full-chain CCUS project operations. It is essential to align all project activities with recognized academic and industry standards. Key references include ISO 14040 and 14044 for life cycle assessments, IEA GHG reports for operational challenges, the GHG protocol for Scope 3 accounting, and ISSB IFRS 2 for climate-related disclosures. Thank you for joining this module. For further collaboration on consulting, research proposals, or professional training, please feel free to reach out via email or connect through the professional network links provided.